Hello, how are you all? My name is Arturo Calderón. I am an agriculture engineer, doctor in horticulture, with a specialty in hydric management of crops and vines. Today, I was invited to give you a keynote on how to improve productivity in European plum orchards by means of efficient water resource management and understanding plant hydric management. First, we want to talk about when we talk about productivity, especially with dealing with fruit trees, is that productivity increase begins with a quite old process, which is domestication, where we take the plants from a national environment or national ecosystems to domesticated plants managed in agro ecosystems. Therefore, the first function in order to improve productivity in a certain way is to create ecosystems adequate that allow a correct adaptation of the fruit crop to destination conditions. Within this increase in productivity or development, in this case of hermaphroditic species, decrease in juvenility, elimination of alternate reproduction, which in case of plum trees is quite important because these are plants that have a genetic tendency towards production of mannerism. But very important emphasis was made on domestication process that began, in the case of orchards or fruit species, nearly 6,000 years ago, with resistance or tolerance to biotic and abiotic stress conditions. At this moment, it is very important to have a clear context of when we are talking about developing a European prune production for dehydration in a context of climate change and in a context where especially biotic limitations will be very relevant when it comes to evaluating orchards' profitability. In case of European prune, in order to have a framework, we have to think that today we have nearly 12,400 hectares planted in our country, highly concentrated in the central area of Chile. This area that has changed a lot in terms of its water regime. Previously, it was a rather Mediterranean climate with clear seasons, but today it is a rather semi-arid zones. About 70% of the European plant production is located in the O'Higgins region, and nearly 20% is located in the metropolitan region. So we're talking about areas that are strongly affected today by the climate change, with increasing air temperature, increasing water demand, and unfortunately, water availability for irrigation has been reduced. Climate change predictive models are not very optimistic, and no doubt this is an alert because fruit sustainable production has not only have to think about production and for this or for the next season, but also with projection of an orchard in time. That also was something that happened with the domestication process, and that differentiates fruit growing from the production, for instance, of cereals in yearly crops. Fruit growing is an activity closely related to human settlements, closely related to territory, because this is an investment that will last for several years. Therefore, we must think that our orchard has to be a long-term agribusiness. And unfortunately, these climate change models tell us that for the central zone of Chile, and here we have a work by Nicolas Bambach, and here we can clearly see that there are three different characteristics that will affect water availability in our country, and that will be complex. In case of temperatures, here we have three thermometers, one for average temperatures and the effect that the climate change will have within 30 and 100 years. We can see here the medium term, the average temperature will increase close to 2 degrees Celsius, which is quite a lot. This increase in air temperature will mean not only that we're going to have a more advanced season, in other words, it will accelerate the development of shoots and leaves, but also the evaporative water demand will increase because increase of air humidity plus decrease or maintenance of humidity and increase in vapor pressure deficit is generated. This causes an increase in water demand by orchards. In case of rainfalls, the news is not so negative because this will remain within an average. However, the scenario becomes dramatic in snow accumulation. Today, in the central zone, the snow reserves are nearly 118 cubic kilometers of snow. However, in the medium term, this amount of snow will decrease by about 40% from 118 to 72 kilometers. This means, from a fruit growing planning point of view in the central zone, this means that all these initiatives to package water, conduct water, and use groundwater, although these are very important, it is not at 100% the right solution because water availability is going to be much less because these sources are going to decrease. All this will become a scenario where higher temperature with higher water demand and with less irrigation quota. The plants will be affected no matter what by a water stress condition. Depending on how this water stress or this lack of water is managed, we will have more or less negative effects. In general, we understand the negative consequences, and what we want to avoid in a severe water deficit are that some plant responses decrease in production of fruit quality. Within these responses, the most common and the first one that occurs when plants face severe water stress is sugar and cell growth. It is important to consider that plants, as they are vegetable organisms, need water to expand their cells and overcome resistance of the cell wall. We have to think that plants and each cell of the plant is like having a bag of water. In order to blow, it needs a lot of pressure of air. In case of plants, we need a lot of water pressure, and that is not generated if the plants are not well hydrated. When this happens and there is water stress, the internal water pressure drops first, and all the plant's organs growing at that time stop growing. Therefore, this is a very negative, especially at certain crop stages, where the fruit size is defined. Another effect is stoma's closure. When the plants and the soil is dry, the roots react, sending chemical signals, and the stomas, which are the pores located on the leaves where gas exchange takes place, CO2 input for photosynthesis, but also the output of water vapor through transpiration is closed. Both processes greatly decrease their occurrence when the stomas close and the first transpiration is reduced. And when transpiration decreases, other events begin to occur. For instance, leaves begin to heat up because water lost through transpiration generates what is called evaporative cooling. And when this happens, this allows that leaves, despite the high solar radiation that is falling on them, maintain a temperature that is optimal for photosynthesis. When stomas close and temperatures increase, the leaves, which are naturally adapted to more moderate temperatures to perform maximum photosynthesis between 25 and 28 degrees, are less efficient and they begin to do something that is commonly referred to as breathing. This breathing means that instead of fixing carbon to grow and improve quality, it begins to spend it. Therefore, it has a much less efficient photosynthesis and even it starts to consume those sugars that the plant has worked to manufacture. This obviously, if extended over time, will cause a decrease in the production and quality of the fruit, along with closing of the stoma and temperature increase. The fact that stomas are closed and sometimes for a long time and sometimes when stomas are very close, it means that photosynthesis will drop a lot when this will involve problems to catch CO2. Now, not indirectly due to the temperature increase, but only due to the lack of CO2 supplement to create carbohydrate and generate dry matter. All this water stress is bad? The answer is no, because stress is a response of the plants before a condition. The damage caused will depend on three factors. The first one is stress severity. Not all water stresses are severe. Therefore, The more severe the stress, the more severe the effects will be. The duration as well, depending on the duration of this stress occurring for 1 or 2 days, will be less harmful than stress occurring for 1 or 2 weeks. Of course, the timing or the time when this stress occurs is extremely important. Severe water stress prolonged for a few weeks during the bud induction season can mean a dramatic decrease in flowering productivity and fruit production for the following season. Therefore, the damage caused by water stress is not per se only when the plant enters this physiological condition, but it is a mixture of severity, duration, and time of occurrence. When we have these three components, we can estimate the damage that may be caused. And when we talk about timing at the moment of occurrence, we have to think what are the phenological conditions in order to define productivity and quality of the European plum. In this case, we prepare this adapted chart where we can see, according to fruit growth over time, key phenological events. One of the first ones is the time between flowering and curdling. It happens here between September and the first weeks of October, depending on the area. Now, what happens with this flowering and curdling? This is an extremely important stage because we define the transformation from flowers to fruits. It is a time for the plant under great demand. It's a time when roots also begin to grow. Therefore, carbohydrate supply becomes very relevant, such as during bloom. The plum trees still do not have a sufficiently developed foliage, and there are no leaves supplying this high demand. An adequate flooring and an adequate setting will highly depend on the reserves that the plant has. This is quite important because the difference between fruit trees and fruit trees such as vines or kiwis is that fruit trees distribute more carbohydrate to reserve, which allow them to have a better flowering and rotation for the following season than what a vine does. So it is important to start the season with an adequate water condition that allow plants to begin grow shoots to quickly develop leaves in order to supply the following processes with carbohydrates. Now, what processes are these? The process between curdling and ripe color, that is between October, December, or January, depending on the area. The ripe color stage is when soluble solids begin to accumulate, firmness starts to lose, organic acids begin to degrade, and the fruit starts to get color. This time is very important for this type of fruits because the plum tree has a curve named double sigmoid curve. It means that in the first growth peak, about 60 to 70% of the final size of the fruit is at risk. Therefore, any water stress at this time is going to cause a small caliber. On the other hand, between this and harvest, the fruit is getting ripened. However, during early summer, in other words, by late December or early January, this is a high relevant time for the following season. That is when the buds in the European plant begin with the induction process and then differentiation. This process defines the amount of flowers for the following season. Obviously, at this time, it is extremely relevant that plants have a certain water status that allow them to feed with carbohydrates the demand for future flowers. Subsequently, the fruit ripening season goes from January to harvest, where production of carbohydrates is needed in order to produce good sweetness, good size, and good firmness. Finally, many times, and here I have to emphasize, post-harvest is highly relevant. Oftentimes, there are many recommended cultural practices assuming that because the plant no longer has fruit, its water demand is less. Indeed, it may be lower because generally the harvest in case of the European plum that occurs between March and April, at this time evaporative demand is lower because evapotranspiration has decreased, the sand angle is not the same, therefore water demand is lower. But we still have active leaves, photosynthesis and the production of reserved carbohydrates is required. Therefore, here we have key event that we have to consider with a good water status. Now, what can we do to improve our water supplement in this case? When we say we will have water problems, we're going to have problems in this area. We will have, and in this area, we have several ways, several tools that can help us to meet this objective of improving water conditions in pursuit of a better productivity. First, use more efficient irrigation system, reduce water application in orchards, apply strategies such as controlled deficit irrigation, and use drought-resistant grafting. These are technologies and cultural practices that can help us for fruit growing for what remains of this century. Fruit growing that will be strongly marked by low water availability and high temperatures. Now, can we do something? Well, if we review this fruit census, we can see that for European plum, about 74% of planted hectares of these 12,450 hectares of European plum, today they use technified irrigation, a high percentage of orchards with high efficient irrigation, about 85%. These systems include drip irrigation over 90%, sprinkling micro sprinkler irrigation with 80 to 85%. Therefore, this highly effective system will allow us to reduce water loss due to runoff or direct evaporation from the soil. On the other hand, we still have a margin of action with about 26% of orchards that are still using poorly effective irrigation, such as furrow irrigation or line irrigation. In this case, that is 26% or a quarter of these 12,000 hectares, which still can improve their irrigation efficiency by a technology reconversion. For this orchard, this is not optional, it's compulsory. It doesn't mean that it's a law enforced, but it's mandatory because they are settled in an area where water availability in the coming years will decrease dramatically. How can we also reduce water application in orchards? Well, here is an example. About 70% of European plum orchards are located in O'Higgins. This is Rango, and the calculation of evaporative demand during the season here in red color. We can see that during December, January, and February, evaporative demands tend to be maximum close to 6 millimeters per day. That is high demand for water, and at the end of the season, there will be a consumption close to 7,000 cubic meters per hectare. Here, many people who are listening to this, we apply over 10,000 cubic meters per hectare. If the demand is 7,000 and we apply 10,000, that quickly means that we have 3,000 cubic meters that the plants are not using. Therefore, we still have some room to improve. And how can we do it? For instance, we can define the amounts of water to be applied. There are several ways to do this, but I think the simplest one is to use biometeorological methods, such as the estimation of atmospheric evaporative demand by means of crop coefficients. In Chile, most of the orchards are developed in a traditional way, and this means between 560 plants per hectare Dajan plum with rootstock 26-24 plants from 6 to 5 meters. This is similar conditions to the California, where we established in 2002 this type of orchards. These crop coefficients that are used, the demand of the orchards, and we can do it accurately. The way how we create this coefficient during the season is that this sort of trapezoid where we have an increase matching the increase in foliage. Then we have values close to 1. That is when the foliage is fully covered the ground. There is no more vegetation development. It remains for several months until it declines after the harvest. That is when the plant begins to die and when the leaves begin to lose Not only its stomatal conductance, the stomas begin to close, but also the lips begin to fall and transpiration per plant decreases. There are other ways, such as properly defining the irrigation frequency. The most used method in California and very successful in European plants is using the Schollander pump or using the pressure chamber. It's the same instrument. This pump or pressure chamber, that is what you can see here, is a tool used to measure the water stress level in crop. It tells us when the plant is stressed enough to receive water. In this way, watering decision is not subjective, it is objective. It will respond to the need that the plant has according to this vegetation development, supply of irrigation water, and the evaporative demands from the atmosphere. There are other things that here we have Pedro Fuentes with one of our trials. And here we measure the stomatal conductance, which is the stomach's response before lack of water. That also helps us to understand what is the response of the plants here against water stress. These are tools that have been used for years to precisely define in commercial orchards the occurrence of the irrigation event. However, today new technologies exist. For instance, one of the problems of the pressure pump is that measurements must be made by a trained person, and it is done on a fairly short period of time. Therefore, we have a limited number of measurements in a day. Therefore, it would be great to have a tool that allows us to measure continuously and receive data in a platform, just as we do with the ground humidity waves. This technology exists today, and this is named Microtensiometer. These are sensors inserted into the plant that estimate the water potential, the water stress level in the plant during the day and every day in 24/7. These experiment results on commercial orchards are quite promising. Here we have data from Andrés Olivo. These microtensiometers have been tested, and here we can see the comparison of the microtensiometer, the blue line, against the pressure pump with the red line. And here you can see that the data matching is very high. In other words, these new tools are capable to accurately measure water status of a plant. Now, using these two tools will depend on the purchasing power of the farm and also the objectives they may have in this case. This tool provides continuous measurements, and the disadvantage of this is that it gives us a very localized measurement. And plant water status is very variable within a plot and obviously among plots. It depends on plant's vigor, type of soil, some specific conditions as well, such as root diseases or some other factors limiting water absorption in this case. We have these tools aimed to measure frequencies. We have these tools to calculate demand, and we have new technologies that are not really new. One of these is controlled deficit irrigation. We must understand that this controlled deficit irrigation is a strategy that applies a smaller amount of water than the maximum the crops demand, and with this we can maintain productivity or even improve some quality aspects. Here, this is a very old work by Professor Shackle from UC Davis, showing the effect of two controlled deficit irrigation strategies on parameters that are relevant to the industry. On the other hand, we have the treatment with no hydric stress, assuming that we have water close to the maximum demand. I said 7,000 cubic meters for Renko, and here we have 70, and the goal is to maintain the water status of the plants at minus 0.5. This is to have a very high water status. The results of this strategy can only be achieved if I have enough water. That is to have a fresh yield of 40 tons, dry yield of 14 tons with a very good yield, a fresh dry conversion of 3, and therefore we have these results with the very abundant water conditions. But what happens if we lack water? Well, the second strategy is applied when we have a low water level, and that is to use this late moderate water stress. In this case, we can see that fresh yield does not differ statistically, that is same, even though the numbers are different. It equals fresh performance compared with full irrigation, free demand. It is 41 versus 39, the same production for fresh. For dry, it is exactly the same, 14 dry tons, which is precisely the objective of the stock. How much does it affect to reduce water demand compared with these production parameters? Therefore, we have the same dry performance. The conversion improves slightly. For water amounts applied here, there is a huge decrease, big water savings, from 7370 to 4490. Now, if the water is even more limited, we cannot even generate a water condition of minus 1.4 megapascals. That is trying to maintain water conditions with Schollander pump at that range. Optimum water condition is minus 0.5. Minus 1 plus negative means more stress, nearly 3 times more. If I don't have water to keep this stress level, we get severe late moderate water stress. In case of European plant, fresh production decreases, which is hard for those exports with a mixed production, with production of dry fruit and a small percentage for fresh fruit. This strategy may impact on fresh performance. What happens with dry? Again, the similarities tells us that dry fruit performance is the same. Therefore, this late moderate water stress does not impact dry production, and it does improve dry fresh conversion, obviously making drying costs lower or field drying time shorter, and the amount of water applied is much less, with savings close or higher than 50%. It goes from 7,000 to 3,000 cubic meters per hectare. It's a high saving. But in order to achieve this, we go to the previous concept. It's a strategy based on severity of late water stress in this case. Therefore, it is late and it has a time of occurrence, and it is far from the flower induction period for the following season, far from the 70% of the final size, and it has a duration as well. So these are accurate strategies. It is not just stop watering. It means stop doing it and monitor how water conditions evolve. Now, what happens in commercial orchards? We did this study with Agromillora and Olivos Riego and the University of Concepcion in a new super high density orchard that is a new way of producing. What happened with the percentage of falling fruits and controlled deficit irrigation? What we can see in this chart is the conventional density and plants with super high density that a deficit irrigation, those are the green bars, has a percentage of falling fruit very similar to that of traditional irrigation, those are the red bars. In other words, drying the plants with moderate deficit irrigation did not affect the percentage of dry fruits. And therefore, this is very important, as the fear many times we have when stopping watering is that fruit aging will be impacted. If this is controlled, that will not happen. Another thing that is important is to evaluate how some quality parameters are impacted. This is a test made in a super high density orchard, and the result was that fresh weight was not impacted. Fruit shape was not impacted, neither in the equatorial or polar diameter, which is important for fresh consumption. But it's important for dry consumption because in the concept of European plant, the fruit has a shape. Therefore, it's important to maintain not only weight but also the product's shape. In firmness, no differences were found. The concentration of soluble solids was the same, and the covering color, the skin, was exactly the same. Therefore, in super high density tests, we realized that application of deficit irrigation will easily adapt to this new production system. What about traditional systems? The system we have with traditional orchards. In Agrícola Río Peumo, and my colleague Andrés Olivo commercially created a deficit irrigation strategy used for several years, induced by the lack of water. And here we will compare the strategies that I mentioned to control irrigation with a very high hydrate status and moderate late deficit irrigation and a severe deficit irrigation, which is the one the company chose. For late deficit irrigation, severe or moderate severe, used by the Agrícola Río Peumo, this meant applying 4,600 cubic meters of water per hectare. Usually, they applied between 7 to 8,000 cubic meters per hectare, saving more than 40% of water, with water potential ranging from minus 0.5 to a maximum of minus 2 megapascals. That is, severely stressed plants at the end of the season. What is the result? The results we can see here in performance and caliber. And we are focused on, I want you to focus on these green bars. And in the seasons for 2016 and 17, dry production, which is usually 10 tons per hectare, that was maintained. And the caliber, that is between 60 and 70, was also maintained. Therefore, application of deficit irrigation strategies against previous years, where full demand irrigation was made, it managed to maintain yields and non-salt calibers. Therefore, this severe controlled deficit irrigation strategy is possible in commercial orchards. In this case, a company with more than 170 hectares of European plants. And it is possible when we know the severity, the occurrence moments, and the period of duration of stress. These strategies are very relevant, not only from the water point of view, because water still is cheap, but it is also important to evaluate the opportunity cost. If we make an exercise and we say 12,400 hectares are irrigated with 8,000 cubic meters, that means 99.6 million cubic meters. If we use a moderate controlled deficit irrigation, it means using instead of 99, nearly 100 million, we use 60, which saves on 40 million. And how can we use these 40 million of cubic meters? We can irrigate 7,460 hectares of European plants with deficit irrigation. In other words, we could go from 12,000 to about 20,000 hectares with the same amount of water if we apply deficit irrigation. This is called opportunity cost, and it's the most important cost when we use water efficiently. What I don't spend here, I can invest it here for planting berries, walnuts, cherry trees, or hectares of plum trees. More. This is new production technology that can reduce the water consumption, and here we have done this for several seasons, where super high density orchards could use a lower amount of water based on a longer distance among the plants, thus obviously saving labor. In this case, what is most important for us is getting a lower evapotranspiration. And eventually, the rootstocks used in this system may also have a high tolerance, which is the focus of this study. Finally, as a conclusion, we must say that climate change is going to be unsustainable. Meet the maximum demand in the whole area planted with fruit trees in Chile. Therefore, now we need management strategies in order to face this lack of water. Traditional orchards that we have in Chile, those 12,400 hectares, most of them are traditional orchards, large plants with a lot of water. Therefore, it is very important to change the system or the irrigation systems. In order to change the irrigation system, we have new strategies such as controlled deficit irrigation that will allow, by using hydrate stress, to continue the business. This is quite important because if extreme water limitation arises, we can generate a water stress level such that although it may affect the caliber of fresh plums, it will not impact on dry caliber. This is an advantage from the dehydration point of view. because it will allow to produce the same quantity and quality, but with much less water. These new technologies for these orchards and other production system can reduce not only labor cost, but also water requirements, which is extremely important. No production system is going to reduce water consumption per se. To reduce water consumption, we have to irrigate less. Therefore, we have to optimize irrigation systems and the way how they are applied. Well, thanks for your invitation. I hope that this short talk has been useful for you. And well, that's it. Thank you very much for your attention.